This is the story of a new, effective way for man to recover natural resources, valuable natural resources that are often locked deep beneath the surface of the earth. This is the story of how atomic energy is applied to this important problem. This is the story of the atom underground. Natural gas, one of our important sources of energy, is used by millions of households and industrial customers in many parts of the country and the world, and the number is expected to increase greatly. Natural gas is found underground at depths ranging from a few hundred feet to several miles. To make natural gas available for consumption, a well has to be drilled to the rock formation containing the gas. These gas-bearing areas are often referred to as reservoirs, which leads some people to think that the natural gas, or oil, is gathered in caverns. But that is not the case. Natural gas occurs in rock that is frequently as solid as concrete. In this rock, the gas exists under tremendously high pressure in tiny spaces that may be invisible to the unaided eye. When a gas-bearing formation is tapped, the gas, under high pressure, flows to the well and rises to the surface. In some fields, the gas-bearing rock is highly porous, and the tiny channels between the pores permit a relatively free flow of the gas to the wellbore. However, great quantities of natural gas are also contained in very tight formations. The pathways connecting the spaces that hold the gas may be so narrow that the flow of gas is greatly reduced or cannot flow to the wellbore at all. Therefore, for many years, it was the practice to use nitroglycerin in these formations, detonating it to cause cracks to stimulate the flow of gas to the wellbore and increase the total amount of gas recovered. The search for even more efficient methods to stimulate the production of natural gas and oil suggested the use of the enormous energy of atomic explosions. The U.S. Atomic Energy Commission, in line with its Atoms for Peace program, had established a research and development program in the peaceful uses of nuclear explosions in 1957. The program was given the name Plowshare, expressing the hope that Prophet Isaiah's prediction for peace may, after all, come to reality. Underground nuclear explosions will take their place along with conventional chemical explosions and most likely achieve an ever-growing importance. Enormous energy, compact and easily transportable, relatively inexpensive. This is the new power tool that Plowshare will add to man's resources to do jobs never before economically practical or even possible. To illustrate, a nuclear explosive of 10 kilotons, that is, the equivalent of 10,000 tons of TNT, could be as small as 1 foot in diameter and 3 feet long. The price could be about $350,000. However, in contrast, 10,000 tons of TNT would fill a large sphere more than 80 feet in diameter and would cost about $5 million, more than 15 times as much. Furthermore, if one increases the nuclear yield 200 times, up to 2 megatons, the nuclear package could be only a little more than 3 feet in diameter and 10 feet long, and the price doesn't even double. But to increase the yield of TNT 200 times, one would have to increase its size 200 times, ending up with enough TNT to fill thousands of freight cars. The price of the TNT would increase to more than $1 billion. This was the world's first experiment using an atomic explosion for industrial purposes. This project of the Plowshare program received the name Gasbuggy. The place, New Mexico. Objective, to study the use of underground explosions in a gas-bearing formation to stimulate the flow and production of natural gas. In December 1967, a 26-kiloton nuclear device was detonated 4,240 feet underground. Cooperating on the project were the U.S. Atomic Energy Commission, the El Paso Natural Gas Company, the Bureau of Mines of the U.S. Department of the Interior, and technical direction came from the University of California's Lawrence Radiation Laboratory. The Gasbuggy experiment showed that the nuclear detonation vaporized the surrounding rock, creating a giant cavity and fracturing the formation in all directions. In about 1 minute, the ceiling of the cavity collapsed, resulting in a rubble-filled chimney. Extensive fracturing through the gas-producing formation provided many new channels for the gas to flow to the wellbore. Estimates indicate that the gas flow was increased many times. In only a few months, Gasbuggy produced as much gas as nearby conventional wells had developed in years of production. With the results of Gasbuggy still being analyzed, the government and private industry, this time represented by the Austral Oil Company and CER Geonuclear Corporation, are cooperating in a second gas stimulation test involving a 40-kiloton detonation 8,400 feet underground in Colorado. Project Rulison. What will be the effect on gas stimulation of a bigger detonation at greater depth in a different kind of gas-bearing formation? Even preliminary answers are encouraging. Other gas stimulation studies are in development, showing that the new technology has solid commercial promise. Similarly, nuclear explosions may be useful to increase oil reserves. A nuclear explosion could also be used to improve the flow of oil through oil-bearing rock formations. This would result in greater total oil recovery than is possible by conventional means. Thus, marginal oil reserves become economically profitable. Atomic energy may be used not only in production, but also for storage of natural gas and oil. The flow of gas from the producing wells to the consumer is subject to considerable change due to the irregularity of demand. Therefore, storage facilities have to be provided near the consumer market to store the surplus gas when consumption is slower than production. But in winter or in other times of peak demand, surplus can be released to the users. Above-ground storage is very expensive and often unattractive. Natural underground storage is already at capacity. Again, industry is looking to the Plowshare program for the answer. A concept has been developed for using nuclear explosions to create underground storage reservoirs. Natural gas can be pumped under pressure into the chimney of broken rock, and large quantities could be further stored in cracks and fissures extending from the chimney. About 500 million cubic feet of gas could be stored under pressure in the void space created by a 25 kiloton explosion. Tremendous amounts of gas could be withdrawn from the chimney in a single day to meet peak demands, enough to supply the heating requirements of thousands of homes and factories on the coldest day in winter. Crude oil and other petroleum products could also be stored in a cavity deep below the earth created by a nuclear explosion. Water, too, could be accumulated in similar cavities. And even wastes or harmful products could be safely disposed of deep underground in this way. Oil shale, next to coal, is the second most abundant fuel resource in the United States. It is more plentiful than oil and natural gas, but no economical way has been found to get the oil out of the shale. Oil shale, which does not contain liquid oil, is a most unusual soft rock that burns. When it is heated to about 700 degrees Fahrenheit, it decomposes into liquid oil, similar to petroleum, gas, and a coal-like residue. Other studies in the Plowshare program will investigate how underground nuclear explosions can make the use of oil shale possible. Conventional production methods of oil shale encompass two phases. First, the mining. Secondly, the retorting, that is, the heating to decompose the shale to extract the crude petroleum. The atomic technique would eliminate the costly mining and above-ground retorting. The nuclear plan is to first fragment the oil shale underground with an atomic explosion, and then to heat it, decompose it, in place, thousands of feet underground. The crude oil, which drips out from the heated shale, would then be pumped to the surface. This method may, at long last, permit the great energy locked in oil shale to be useful to man. The mining industry expects other promising developments made possible by Plowshare. The unprecedented power of nuclear explosions may fracture hard rock and produce a chimney of rubble or a series of such chimneys. The fractured material may then be recovered by conventional mining techniques. The ever-increasing demand for copper, especially in communications, brought together two technologies: the old art of the leaching of copper and atomic age underground explosions, all adding up to the creation of vast new mineral resources. Leaching is the process of extracting minerals from an ore by dissolving them in a solvent, then removing the mineral-filled solvent from the undissolved materials. Later, the solvent is processed and the minerals are recovered. As the demand for copper and minerals increases, marginal mineral sources have to be used. The Plowshare program is pointing to a way to use marginal sources in its project Sloop, being developed in association with the Kennecott Copper Corporation. The first step is again the underground explosion in a marginal copper ore body. The leaching would be performed underground. The ore is not brought to the surface. The leaching solvent runs through the broken ore, dissolving the copper. The copper-bearing solvent solution gathers at the bottom of the chimney of the fractured rock. This solution is pumped to the surface, where the copper is separated out of the solution. This nuclear technique may apply to a wide range of mineral resources in the future. But all uses are not industrial. The placement of these core samples and the installation of this neutron wheel deep underground demonstrate another scientific facet of underground atomic explosions, the discovery of new elements and the production of isotopes. Of course, nuclear reactors in our laboratories produce radioactive materials which find many uses in medicine, industry, agriculture, and other areas of science. Radioactive materials, tracers, are created in a reactor by exposing them to a stream of neutrons over a period of time. However, during the split second of an underground explosion, a tremendously large quantity of neutrons is released instantaneously. Radioactive target elements placed near the explosion absorb some of this flood of neutrons and are transformed, changed, into different, heavier elements. Thus, the so-called split-second reactor, with its intense stream of neutrons, makes it possible for the nuclear physicist to achieve the age-old dream of the alchemist, transforming one element into another. But while the ancient alchemist attempted to create gold, today's nuclear alchemist finds it more rewarding to discover new elements, valuable elements and isotopes heavier than any of those known. Fermium-257, named after Enrico Fermi, was the heaviest metal produced in this way in the United States. The mass-energy relationship, first stated by Einstein, is very obvious in an underground nuclear explosion. The mass of the explosive releases energy which shatters tons of rock and causes seismic motions that can be registered many miles away. The explosion creates tremendous heat which vaporizes the rock in the center of the impact area. Because these explosions produce radioactivity, safety precautions by radiation monitoring and analysis of weather conditions are assured before underground nuclear explosions are executed in areas where little damage to structures can occur from ground motion. Inasmuch as the explosions occur deep down in the earth, there is no release of radioactivity to the air. Thousands of feet of rock act as a protective shield. Constant monitoring detects unlikely radiation leakage through well bores and instrument pipes, or possible pollution of subterranean water. In another part of the versatile Plowshare program, nuclear explosions less deep underground are conducted with similar attention to public safety. Plans are being studied for geographical engineering, nuclear explosions for the fast economic creation of mountain passes, harbors, water management, surface mining, and others. And perhaps even a new sea-level canal across Panama. Experts believe these ambitious plans will gain reality in the 1970s, using special explosives and special emplacement techniques to minimize radioactivity, reducing and trapping most of it safely underground. In the meantime, nuclear explosions for underground engineering are becoming a reality of our industrial life through the magic of the atom.